right, thank you very much for the introduction, Garrett. Thanks for having me, everybody, and I hope that this is really informative and entertaining and interesting. And by all means, at any point throughout, type your questions into the chat. I have it open on my screen, or certainly if you want to open up your microphone and do that as well, I'm always open to that. I love having interaction with students. I love the opportunity to hear what your questions are. I'm a big fan of students in my classes at school driving the curriculum. And if I'm saying something that you want to know more about, or a different direction you want to go, by all means, jump in anytime whatsoever. So the topic that people from the physics UFV PSA, Physics Student Association, had suggested was the history of astronomy. And so I have a presentation here that deals with that, and it's one of my favorite topics because because we've come from a very weird place. And what's unusual about the history of astronomy is we are still in a place where we're dealing with people questioning whether or not the Earth is round or flat. Did we really go to the moon? There's still skepticism about space, and I think it's based on a lot of we just don't know. We just have never been taught. So allow me to teach you a few things. So I wanted to start with this image right here. This picture is of my mother's family farmhouse. It was built in the early part of the 1900s. My grandfather built this house, and my mother was born in that house. This is it seems odd that 2 generations before where you are, people were being born in conditions such as this. Of course, today is very common in hospitals, obviously, but you know, we're not that far removed from horses and buggies and wondering if we'll ever fly, and you know, wondering what the night sky is all about. And so this sheds for me a light of perspective. It's what we know about space is very, very recent in terms of the sciences. What we know about the universe really is a brand new thing. Even my own mother's lifetime, if she walked out of the door of that house, or if she looked out of that 2nd floor window, which was her bedroom, when she was a young girl in the Saskatchewan prairie, she would have looked at the stars and she would have said, "There is the universe." When in reality, what she was looking at was the maybe 1,000 or 2,000 stars that are visible from Earth on a dark prairie sky that are all within 100 or 200, maybe 500 light years. And that's a fraction of a percent of the size of the galaxy, let alone the universe. Now, at the time, the sky might have looked like this. And I'm sure it still does. If you just get away from the city, it still looks like this. I was in, every summer I take these amazing kayaking adventures up on the coast of British Columbia and off Vancouver Island and up in Desolation Sound. And this past summer, the night sky was so dark where we were camping. It was so dark that the planet Jupiter was reflecting off of the ocean. Now, I've seen the sun reflect off the ocean, and I've seen the moon reflect off the ocean, but I had never seen a planet reflect off the ocean. And so it's a real privilege to get away from the city and see a sky that actually looks like what you're seeing. And when people would look at the sky back in even the beginning of the 1900s and into the 1910s and 20s and into the 30s, in the era where my mother was born, they would think that that these objects were seemingly islands of stars in and of themselves, as if they were separate from our own galaxy they seem perhaps to be a galaxy beyond ours. And he was able to figure out a way to determine how far away they were. It's based on a type of star. Maybe you've heard of it. It's called a Cepheid variable. They're a type of star that will grow and dim in their luminosity over time. And it turns out there's a relationship between the time it takes for them to move from bright to dim and back to bright again, related to their luminosity. And it turns out that a Cepheid variable, if the period of time is quite short, it's a very bright star. But if the period of time is quite long, it's a dimmer star. Well, this makes a difference because imagine you're trying to figure out how far away a car is at nighttime. It can be done if you have a light meter. Now, what you'd have to do is you'd have to measure the light as it is right up close to you. Just like this light here is right in front of my face, I can get a light meter reading on that. Well, if you took that same light source, maybe the headlights of a car, and moved them far away, if I could get a reading with my light meter on that light from the distance, I could then use some math and figure out how far away it is based on what we call the magnitude. So I have the light right in front of me. That's what I'll call my absolute magnitude. That's absolutely what it is. But if you move it away, it looks this bright, probably dimmer, of course. We call that apparent magnitude. So the difference between the apparent and the absolute magnitude can help me calculate how far away something is. And Edwin Hubble was able to do this with Cepheids. He knew how bright the star actually was based on its periodicity in its rising and falling in luminosity. Now, by the way, not all stars do this. Cepheid variables are a unique star. Not every star is a Cepheid, but there are Cepheids, and he was actually able to find Cepheids in these white nebulae. And when he did the calculation, he found that these galaxies, he came to be called, were far further away than anybody had ever imagined. And almost overnight, now really it was probably over 5 or 6 years, but almost overnight, Edwin Hubble took the universe from what my mother would look at out her bedroom window on the Saskatchewan prairie and expanded it from just the view that you see at night to something perhaps you might call far beyond comprehension. He expanded the size of the universe with his research, and it basically blew everybody's minds. They had no idea that the universe was as big as what he was suggesting. But he did one more thing that was extremely significant. And using, again, this amazing information that the universe sends us, the universe speaks to us in the form of its light. We don't need to go to the stars. The stars really come to us in the form of their light. And Edwin Hubble was smart enough to notice that the universe was speaking to us, and he interpreted the language of the stars. And in this language, he read that the light was shifted in the spectrum, and particularly the spectrum of hydrogen is the one that he focused on because hydrogen is the predominant element in the stars. And if you look at the light of hydrogen through a spectroscope, it breaks it down into 4 distinct colors, a couple of shades of purple, a shade of green, and then another shade of red over here. And as it looks in the lab, it appears in a certain spot. But when he looked at it in the through the light from these distant galaxies, all of the light was shifted just a little bit towards the red end of the spectrum. And he began to question what this meant, there had been well understood the Doppler effect. Of course, if a sound source is moving away from you, the sound is dropped a tone because the sound waves stretch as the sound source moves away from you. But if the sound source is moving towards you, the sound waves are compressed, and the compression raises the tone. And so you get the typical, ding, 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 right? The sound of the Doppler effect. But does the Doppler effect apply to light as well? Because if it does, being red shifted means that the galaxies are moving away, because red is at the longer end of the spectrum. It's closer to 700 nanometers as opposed to blue, which is around 400 nanometers. And he described for the first time what's known as red shift. Red shift is a clear demonstration that the universe is expanding. Here's the spectrum of hydrogen as I was describing it. The work that he did through the 1920s, about a decade he worked on this, and during that time he studied, they say, about 50 galaxies. There's, of course, in the visible universe, 1 trillion galaxies. There's 1 million galaxies. He looked at 50 of them, and every one of them was red shifted, which implied that the universe seems to be moving apart. Now, at the time, there was a very strong opponent to the idea that the universe was expanding, and that was none other than Albert Einstein, who, like most scientists, was a staunch static universe theorist. The notion that the universe had no beginning, the universe was constant and unchanging. In fact, when Albert Einstein worked on his theory of general relativity, he said, or he realized that the math indicated that the universe can't be standing still, that the fabric of space-time warps and curves due to the masses that exist within it, the stars and the galaxies and the planets. And so, therefore, objects will naturally fall into these gravitational wells, and there'll be motion towards more gravitational regions than others, and therefore the universe will be moving. And Einstein was so unimpressed with this conclusion that he decided that he'd counteract it by fabricating a value which became known as the cosmological constant. It really was a fudge factor that he placed within his equations to show that the universe did what he believed it should be doing. It's not good science. He cheated in a sense. And so when Hubble came along and said, well, I think the universe is expanding, it blew everybody's minds, and including Einstein's. And so there was, in fact, several meetings between Hubble and Einstein. And Einstein was an intimidating character to have a debate with. Hubble is well thought of as a very good scientist, but he probably himself would admit he was no Einstein. He never won the Nobel Prize. At the time, in the 1920s and 30s, the Nobel Prize wasn't awarded for astronomy discoveries. And so he didn't get it. He certainly deserved it. But when Einstein and Hubble got together, they debated. And it was not until another fellow by the name of George, I'll just go back to this for a sec, George Lemaitre came along, and he was a priest in the Roman Catholic Church, but he was also a scientist. And this was a wonderful opportunity for the blending of philosophies, science and religion. And Lemaitre, a man of the cloth, but a scientist as well, fully accepted the notion that the universe was expanding. He actually formulated a theory around the red shift and the velocity of the galaxies. You see, here's the deal. If the galaxy is closer based on the distance calculated from Cepheid variables, it also appeared to be slower. You see, the more red shifted, the faster you'd be going. And so you had these two parameters. As the distance got greater, the velocity got greater. And what you got was this beautiful sort of linear line that can be described as y equals mx plus b. And m, as you know, is the slope of a line. And that line, that slope, can be used to calculate the age of the universe. And the age of the universe, according to Lemaitre, was in the billions of years, but significantly, it did have, it seemed, a beginning, a moment of creation, that point when the galaxies would have been all together at one point at the beginning of time. And so thus was born the theory of the origin of the universe. Really, this came from the work of Edwin Hubble. And then followed up by the mathematics of George Lemaitre, and ultimately the agreement of Albert Einstein. By the end of the late 1930s, there was, ironically, a discussion held on the BBC radio show where a British astronomer was being interviewed. His name was Fred Hoyle. And Fred Hoyle was asked, what do you think of this new theory that the universe is expanding, it had a beginning and is getting larger every day, the red shift? And Fred Hoyle said, it's ridiculous. They don't even have a name for this theory, for Pete's sake. What are they going to call it? The Big Bang? Well, of course, this makes it into the media, and next day, perhaps in the newspapers. And everybody said, you know what, that's a pretty good name, and it stuck. And so poor Fred Hoyle, who was a staunch static universe theorist, actually is the one who named the theory the Big Bang. And I'm sure he went to his grave wishing that he had never done that. And so the expansion of the universe was well established. There was one more thing that was required to cement that theory. One of them was we needed to get a better way of figuring out the size of the universe. And Edwin Hubble was very correct with his calculations in terms of the distances, in that the Cepheids did tell you that the universe was bigger than they thought it was, but his actual distances, I believe, were off by something like a factor of 7. Which meant the universe was actually far bigger than he thought it was. Later on, they developed other ways. For instance, the Type 1a supernova has become the standard candle of the universe. Basically, what this means is it's an easier object that can be used to determine distance. We know precisely the luminosity of a Type 1a supernova when we find them. And every time we find them, this is a significant moment because it refines that slope. So don't forget that slope is distance against velocity. And every time you affect the distance, you change the slope just slightly. And when you change the slope, then you change the amount of time it took to get to where we are today. And that changes the age of the universe. And this was on display maybe 4 years ago when it was announced that the universe, the age had been adjusted by about 100 million years. It went from 13.7 billion years to 13.8 billion years. And so the universe got older, or maybe our understanding of how old the universe is changed because of our better assessment using Type 1a supernovas. And so then you end up with, and maybe that's been about a half an hour of information. Let me just wrap up with a couple of thoughts. The Hubble Ultra Deep Field image was taken. No, Hubble didn't get the Nobel Prize, but he did in fact get a telescope named after him, and perhaps you could say that the Hubble Space Telescope is perhaps the most important piece of scientific equipment ever built. It was launched in 1990. They got it working properly by about 1992, and it's been orbiting Earth ever since. And this image that you're seeing right now is one of the more famous images that the Hubble took. What they did was they opened the shutter to the camera, a very sensitive camera up in space, and allowed it to stare at a point in the sky that's otherwise blank, seemingly. And they exposed the film, or not, wouldn't be film, but a digital image for, I believe, 11 straight days. And after the 11 days of continuous photography, this is what was produced. Every speck and light and image and blur and smudge, everything you see in this image is a galaxy, not a star, but a galaxy, a collection of hundreds of billions of stars. So just in this image alone, there's something like 10,000 galaxies, each with having 200 billion stars, which raises a fascinating question: are we alone? It's almost more absurd to say that we're I always get this one mixed up, where it's almost more absurd to say there is no life out there than to say that there is. Of course, we don't know, and likely with the distances that you're looking at here, we'll never cross those barriers, hundreds and thousands of light years. But certainly the odds are that there probably is something out there that's maybe looking back at us. I'll end with this slide. In the end, there was, and there's a bit of a video here. Let me just play this video. You know, you see clouds. Sometimes you see the sun poking through. And you look beyond the clouds, you see the stars. And if you look beyond the stars, galaxies. And if we put the most powerful telescopes on the most distant objects, what we see are seemingly an endless array of galaxies that seem to go and go and go. But is there a point where we can see even beyond the galaxies? And in fact, there actually is. Back in 2004, a satellite was sent up to take a picture of the origin of the universe. And if you look out beyond the clouds, beyond the stars, and beyond the galaxies, what you see is an energy that seems to have a uniformity in its non-uniformity. It's anisotropic. You see, it's kind of like the dew that you see across the top of this surface. There's a uniformity in its non-uniformity. There doesn't seem to be any one spot that is more or less concentrated with the dew drops. But there must be something that's causing the drops to form more here than here. That's anisotropy. And without an anisotropy in the universe, we wouldn't have had stars form or galaxies condense. What the astronomers believe should be the case is this: since we've got galaxies everywhere in the universe, that meant that the universe couldn't have formed with an even distribution of energy. There had to be a certain amount of unevenness to it. There had to be regions of the universe where some areas were hotter and some areas were cooler. The cooler areas would have been where the galaxies would have condensed. If that weren't the case, then what we observe would make no sense. So when the universe was observed closely in 2004 with the Wilkinson microwave anisotropy probe, what it saw was exactly what they expected to see, which was an uneven distribution of energy. If this weren't the case, what they would have seen would have been a wash of stars everywhere or no stars at all. All right. And sort of thus is endeth the lecture on the history of astronomy. And as you can well imagine, I've touched on something that's so significant in the 20th century that uncovers the way the universe maybe started. But you must understand, of course, there's so much more about the history of astronomy that but you just cannot learn it all. It's astronomical, the information that exists about the universe. And It's only through your own hunting and searching for answers and attending things like this and reading books and watching videos, and you'll learn, and eventually you'll come to understand the enormity of the universe and where it all came from.
First of all, thank you for the presentation. I think that was an absolutely great representation of where things kind of started with basically the universe in general, and how we've kind of come to where we're at now.
Yeah, no, I was wondering for that. You were talking about that Betelgeuse going supernova.
Yeah.
That's in our own galaxy. Would
Oh,
we
yeah.
be able to see that happening?
And it will be a remarkable event because it is in our galaxy. In fact, it's close. Our galaxy is 100,000 light years across. Betelgeuse is only 500 or 600 light years. So 500 out of 100,000 is very close. Even though a light year is about 10 trillion kilometers. So 500 times 10 is 5,000. So it's actually 5,000 trillion kilometers away. So it won't damage us. We're not in any danger, but we'll have a spectacular view. It will be visible, probably, they say, for about a week, even in the daytime. Now, last year, about this time, Betelgeuse was doing some very unusual things. It was sort of pulsing. It was growing and dimming, and it's growing and dimming. And they're thinking, oh my gosh, it's like the volcano is about to blow. And then it settled down. And a lot of people thought it was on the verge of blowing up last year at this time. And but it still hasn't. And the truth of the matter is, stars don't operate on human lifespans. They operate on stellar lifespans. Well, a stellar lifespan is measured in millions, if not billions of years. So somebody said, Betelgeuse is going to blow up any day now, as long as you're okay with any day being 100,000 years. So, but we'll have a great view if it, if it happened now. It'd be fantastic.
I'll hope I can see it then.
Yeah, try to live long enough to see Betelgeuse blow up.
So my question was maybe the question to close off the evening. So I see most of the names here are familiar. We're either math students or physics students. So if you had any advice for a young scientist today, what would that piece of advice be?
Well, physics and math, like, to me, science has these certain great quests. One of the quests that science is faced with right now, I would say, is the exploration of space and getting to these other places in our solar system that seem to be habitable. Obviously Mars, but not just Mars, but Europa and Enceladus orbiting Saturn. So then the other one, so before I fully answer your question, the other one I'm thinking of is our own planet. There's a large scientific issue that we're dealing with right now, and that is climate change. And these are problems that need scientists to come up with creative, like imaginative ways of dealing with the energy problem, or the recycling problem, or carbon capture, or how are we going to mitigate ocean acidification. And all of these things are happening because we've gone through 150 or 170 years of unimagination. We're not thinking outside the box. We discovered oil. Great, let's burn it for everything. But we're at a point now where that's resulted in climatic crisis. We need creative, scientifically trained people who are going to say, there's a new way of doing things, and we've come up with it. I'm a really big fan of right brain, left brain. Don't just study science, but paint and write poetry and get creative with your hands and build things. And as you're outside, look around and go, you know what, I see what's happening here. it's this. I believe that science is going to be the solution to all of these great issues. You think of Elon Musk. For decades, rockets launched and then were discarded. It took an imagination of Elon Musk to say, there's got to be a better way. We're going to land them and refuel them and use them again. I'm sure everybody just laughed at him, but he's the one laughing now. And same with his whole business with electric cars. I think the advice is find yourself a mission. Don't worry as much about your major, but what's your mission going to be? Once, like the most important thing you can do in your stage is to figure out what's the most important thing that you think is needing attention. What's your major transformative purpose in life? And then you figure out a way to fix it, whether that's the Amazon or the oceans or climate or transportation or energy or space exploration. It's got to be based on what you're passionate about. Don't chase the dollar. Don't chase the job. Chase the mission. And I think that's going to result in a far happier, more productive life.
Thank you.
Hey, you're welcome.
All right. Well, I think that last little bit you had there was inspiring. One, like it puts a very much larger perspective, at least to some of us older students here that are trying to figure out a way and what we're going to be doing at the end of our 4 or 5, 6 years of university education, and say, okay, well, I've got a degree. What do I do? What do I do now? So I think that's some great advice. And with that said, I'll let you go for the night, and everyone have a great night.
Thanks a lot, Garrett. Thanks for having me.
Thanks, everybody. Bye.
Bye now.